Welcome back. This is part 2 of this lesson. We're going to continue immediately from the end of part 1, so let's get started. Now that you know the structure of a segment, let's take a look at how it's used within TCP. Let's take a few minutes to look at the architecture of TCP. TCP, like IP, is used to allow communications between two devices. Let's assume a laptop and a game server. TCP is connection-based, so it provides a connection architecture between two devices, and let's refer to these as the client and the server. Once established, the connection provides what's seen as a reliable communication channel between the client and the server, which is used to exchange data. Now let's step through how this actually works now that you understand TCP segments. The actual communication between the client and server, this will still use packets at layer 3. We know now that these are isolated. They don't really provide error checking, any ordering, and they're isolated, so there's no association between each other. There's no connection as such. Because they can be received out of order and because there are no ports, you can't use them in a situation where there will be multiple applications or multiple clients, because a server has no way of separating what relates to what. But now we have layer 4, so we can create segments. Layer 4 takes data provided to it and chops that data up into segments, and these segments are encapsulated into IP packets. These segments contain a sequence number, which means that the order of segments can be maintained. If packets arrive out of order, that's okay because the segments can be reordered. If a packet is damaged or lost in transit, that's okay because even though that segment will be lost, it can be retransmitted and segments will just carry on. TCP gives you this guaranteed, reliable, ordered set of segments, and this means that layer 4 can build on this platform of reliable, ordered segments between two devices. It means that you can create a connection between the client and the server. In this example, let's assume segments are being exchanged between the client and the game server. The game communicates to a TCP port 443 on the server. Now this might look like this architecturally, so we have a connection from a random port on the client to a well-known port, so 443, on the game server. So between these two ports, segments are exchanged. When the client communicates to the server, the source port is 23060 and the destination port is 443. This architecturally is now a communication channel. TCP connections are bidirectional, and this means that the server will send data back to the client, and to do this it just flips the ports which are in use. So then the source port becomes TCP 443 on the server and the destination port on the client is 23060, and again conceptually you can view this as a channel. Now these two channels you can think of as a single connection between the client and the server. Now these channels technically aren't real, they're created using segments, so they build upon the concept of this reliable, ordered delivery that segments provide and give you this concept of a stream or a channel between these two devices over which data can be exchanged. But understand that this is really just a collection of segments. Now when you communicate with the game server in this example, you use a destination port of 443, and this is known as a well-known port. It's the port that the server is running on. Now as part of creating the connection, you also create a port on your local machine which is temporary. This is known as the ephemeral port. This tends to use a higher port range and it's temporary. It's used as the source port for any segments that you send from the client to the server. When the server responds, it uses the well-known port number as the source and the ephemeral port as the destination. It reverses the source and destination for any responses. Now this is important to understand because from a layer 4 perspective, you will have two sets of segments, one with a source port of 23060 and a destination of 443, and ones which are the reverse, so a source port of 443 and a destination of 23060. 3060. From a layer 4 perspective, these are different, and it's why you need two sets of rules on a network ACL within AWS. One set for the initiating part, so the laptop to the server, and another set for the response part, the server to the laptop. When you hear the term ephemeral ports or high ports, this means the port range that the client picks as the source port. Often you will need to add firewall rules allowing all of this range back to the client. Now earlier, when I was stepping through TCP segment structure, I mentioned the flags field. Now this field contains, as the name suggests, some actual flags, and these are things which can be set to influence the connection. So fin will finish a connection, ACK is an acknowledgement, and SYN is used at the start of connections to synchronize sequence numbers. With TCP, everything is based on connections. You can't send data without first creating a connection. Both sides need to agree on some starting parameters, and this is best illustrated visually. So that's what we're going to do. So the start of this process is that we have a client and a server. And as I mentioned moments ago, before any data can be transferred using TCP, a connection needs to be established, and this uses a three-way handshake. So step one is that a client needs to send a segment to the server. So this segment contains a random sequence number from the client to the server. So this is unique in this direction of travel for segments. And this sequence number is initially set to a random value known as the ISN or initial sequence number. So you can think of this as the client saying to the server, hey, let's talk, and setting this initial sequence number. So the server receives this segment and it needs to respond. So what it does is it also picks its own random sequence number. We're going to refer to this as SS. And it picks this, as with the client side, randomly. Now what it wants to do is acknowledge that it's received all of the communications from the client. So it takes the client sequence number received in the previous segment and it adds 1. And it sets the acknowledgement part of the segment that it's going to send to this CS plus 1 value. What this is essentially doing is informing the client that it's received all of the previous transmission, so CS, and it wants it to send the next part of the data, so CS plus 1. So it's sending this segment back to the client, it's picking its own server sequence, so SS, and it's incrementing the client sequence by 1, and it sends this back to the client. So in essence, this is responding with, sure, let's talk. So this type of segment is known as a SYN-ACK. It's used to synchronize sequence numbers, but also to acknowledge the receipt of the client sequence number. So where the first segment was called a SYN, to synchronize sequence numbers, the next segment is called a SYN-ACK. It serves two purposes. It's also used to synchronize sequence numbers, but also to acknowledge the segment from the client. The client receives the segment from the server, it knows the server sequence, and so to acknowledge to the server that it's received all of that information, it takes the server sequence, so SS, and it adds 1 to it, and it puts this value as the acknowledgement. Then it also increments its own client sequence value by 1 and puts that as the sequence, and then sends an acknowledgement segment containing all this information through to the server, essentially saying, awesome, let's go. At this point, both the client and server agree on the sequence values. The client has acknowledged the initial sequence value decided by the server, and the server has acknowledged the initial value decided by the client. So both of them are synchronized, and at this point, data can flow over this connection between the client and the server. Now from this point on, any time either side sends data, they increment the sequence and the other side acknowledges the sequence value plus 1, and this allows for retransmission when data is lost. So this is a process that you need to be comfortable with, so just make sure that you understand every step of this process. Okay, so let's move on, and another concept which I want to cover is sessions and the state of sessions. Now, you've seen this architecture before, a client communicating with a game server. The game server is running on a well-known port, so TCP 443, and the client is using an ephemeral port, 23060, to connect with port 443 on the game server. So response traffic will come from the game server, its source port will be 443, and it will be connecting to the client on destination port 23060. Now imagine that you want to add security to the laptop, let's say using a firewall. The question is, what rules would you add? What types of traffic would you allow from where and to where in order that this connection will function without any issues? Now I'm going to be covering firewalls in more detail in a separate video. For now though, let's keep this high level. Now there are two types of capability levels that you'll encounter from a security perspective. One of them is called a stateless firewall. With a stateless firewall, it doesn't understand the state of a connection. So when you're looking at a layer 4 connection, you've got the initiating traffic and you've got the response traffic. So the initiating traffic in light blue at the bottom and the response traffic in red at the top. With a stateless firewall, you need two rules. A rule allowing the outbound segments and another rule which allows the response segments coming in the reverse direction. So this means that the outbound connection from the laptop's IP using port 23060 connecting to the server IP using port 443, so that's the outgoing part, and then the inbound response coming from the server's IP on port 443 going to the laptop's IP on ephemeral port 23060. So with a stateless firewall, this is two rules, one outbound rule and one inbound rule. So this is a situation where we're securing an outbound connection, so where the laptop is connecting to the server. If we were looking to secure, say, a web server where connections were being made into our server, then the initial traffic would be inbound and the response would be outbound. There's always initiating traffic and then the response traffic, and you have to understand the directionality to understand what rules you need with a stateless firewall. So that's a stateless firewall, and if you have any AWS experience, that's what a network access control list is. It's a stateless firewall which needs two rules for each TCP connection, one in both directions. Now a stateful firewall is different. This understands the state of the TCP segments. So with this, it sees the initial traffic and the response traffic as one thing. So if you allow the initiating connection, then you automatically allow the response. So in this case, if we allowed the initial outbound connection from the client laptop to the server, then the response traffic, the inbound traffic, would be automatically allowed. In AWS, this is how a security group works. The difference is that a stateful firewall understands layer 4 and the state of the traffic. It's an extension of what a stateless firewall can achieve. Now, this is one of those topics where there is some debate about whether this is layer 4 or layer 5. Layer 4 uses TCP segments and concerns itself with IP addresses and port numbers. Strictly speaking, the concept of a session or an ongoing communication between two devices, that is layer 5. It doesn't matter at this level, I tend to combine layer 4 and layer 5 anyway because it's just easier to explain. But you need to remember the term stateless and the term stateful and how they change how you create security rules. Now, at this point in the OSI model, we have the ability to create a stable, consistent communication channel which is bidirectional between two different devices. And as you'll see in the next video of the series, we're going to build on this in layers 6 and 7, and this allows us to add encryption as well as various application layer protocols. But at this point, that's everything I wanted to cover, so go ahead and complete this video, and when you're ready, I'll look forward to you joining me in the next video of this series.